Okay, so next topic is electrolysis. This is the use of electrical voltage, uh, yeah, applied voltage is what I want to say really, to drive chemical reactions. So far we've been talking about spontaneous chemical reactions. These are usually non-spontaneous reactions where we'll use energy, like a battery, like it shows here, right, to drive a chemical reaction in solution. So electrolysis is the process of using electric current to sort of create a chemical reaction. And so one of the common problems that you're given in electrolysis reaction is to talk about what happens when you electrolyze a molten salt. So let's first talk about what a molten salt is. If you take sodium chloride, for example, and you heat it to its melting point, what it does is it forms an ionic liquid. That's the molten salt. So remember, it'll go into the liquid state. The sodium and the chloride ions move independently of each other in the liquid state. And so basically you have a liquid containing liquid sodium and liquid chloride ions. Now, if you apply a voltage to these, there's a couple of different reactions that you can get to take place. Primarily in pure sodium chloride, though, what you're going to be seeing is sodium ion getting reduced and at these temperatures is probably sodium liquid, but it might be sodium solid because this takes quite a bit of let me go ahead and put liquid in here because I'm pretty sure that's what that is. At the temperatures used to do the molten salt, it's probably forming a liquid sodium metal on the surface, which then comes off. Again, we're using inert electrodes because there's not an electrode that's really robust that you could make out of sodium, and then chlorines definitely couldn't be made into an electrode. So the reason I chose the cathode reaction to be sodium is because sodium's the cation, and the easiest thing to do with a cation is add an electron to it. So that's a reduction reaction. So this is my cathode reaction. Now, on my anode side, I'll have the oxidation of chloride. And typically, chloride oxidation produces chlorine gas, like that. Now I got to balance this, so there'll be 2 electrons here, like that. And so the overall balance reaction would actually be doubling of this, right? And I'll have Na, sorry, 2Na plus C2Cl minus makes 2Na in the liquid state plus Cl2 in the gas state. So this is your overall cell reaction. Typically there's not a barrier between these two. It's just we're thinking about one half of the cell containing the anode and one half of the cell containing the cathode. Now, in order to make this work, we actually make in the electrolytic cell, we make the cathode the negative electrode because this is the non-spontaneous reaction. And what we do is we force electrons into the sodium because normally the spontaneous reaction is to go the other way. Or you can think of it also as pulling electrons out of the chlorine. It both essentially means the same thing, right? We're trying to pull electrons out this way and shove them down this way, and the way we do it is by applying an external voltage because this reaction is decidedly non-spontaneous, which was what we'll see on the next slide. So I've sort of summarized, oddly enough, this isn't balanced. This whole process on this slide, right? Chlorine is the reduction reaction. Oh, sorry. Chlorine is the oxidation reaction, and sodium is the reduction reaction. What I've listed here are the half-cell potentials for the 2 reactions. So the standard reduction potentials for these two reactions. Now, if you remember, right, the chlorine reaction is the one that's at the anode. So what I end up having to do is flip this reaction and change this voltage, and then when I add them together, I get negative 4.07 volts. So in this electrolytic cell, the basic voltage that you need to make this reaction work is 4.07 volts, based on this calculation here. Now, you oftentimes when you're doing electrolysis, you can use higher voltages. And what a higher voltage actually does in an electrochemical reaction is it speeds up the rate of the chemical reaction. So higher voltages can make it go faster, but then there's some other issues you have to think about, like heat dissipation. These solutions can get hot. They're already hot, but they can get even hotter as you're trying to do the electrolysis reaction. So that's one concern. And the other thing that people are often concerned with in electrolysis reactions is side reactions, other things going on. Because as you make this voltage bigger, basically what you're doing is you're creating the opportunity for reactions that are even less spontaneous to also take place. So anyways, there's a lot of trial and error in this kind of experimentation. But this 4.07 volts is a good starting place when you're doing an electrolysis reaction. Now, I'll be honest with you, I probably shouldn't tell this story, but I did actually have a student one time who became so interested in this that he set it up in his garage. I honestly don't know what ever happened to the student. He was a good student, he passed the class, but I mean like what he did in his future career. But he actually set this up in his garage to try to make sodium metal. He really wanted to have sodium metal. So he had a container of sodium chloride that he heated with a torch, and then again he had like a 12-volt battery, and he had two carbon electrodes. You might be wondering where somebody might get carbon electrodes. His source of carbon electrodes came from my discussion on batteries. Inside the middle of every alkaline battery there is a carbon rod. That's the electrode. And so that's what he was actually using in his electrolysis cell to try to get things to work. And who knows, maybe he eventually got it to work. I just remember telling him it's a little bit dangerous because the chlorine gas is pretty poisonous. And anyways, maybe he got it to work eventually, but he didn't get it working when he was in my class. But he made lots of efforts to try to make it work. He's a pretty funny guy. Anyways. Yeah, so this is an example of an electrolysis reaction and how you calculate sort of the minimum voltage that you need to get the electrolysis to go. And again, electrolysis reactions are non-spontaneous reactions. The other thing that I wanted to point out, again, this is just a reminder of what I said earlier that's important, is the reason we pick the anode and the cathode reactions is because we're trying to find the thing that makes the most sense to happen, the thing that's easiest to do. And so sodium, being a cation already, is most likely to get reduced and be one of my potential cathode reactions, is the reduction of sodium. That means, having said that chloride, because it turns out the halogens can go under a number of different reactions, but the most likely reaction is some sort of oxidation reaction of chlorine, and typically the first guess is the chlorine gas that forms when you oxidize the chloride ion. So again, the cathode is picked based on the metal, and then the anode is picked based on the metal being what's happening at the cathode. Now, we're going to look at a different situation now. We're going to look at the electrolysis of sodium chloride, but we're going to look at it in water. And then when we talk about the electrolysis of sodium chloride in water, one of the things you have to keep in mind is that now you can be both oxidizing and reducing the water. So the typical reactions that we look at are these ones that I've listed here. There's the cathode reactions, right, for the sodium, which we had before. and the anode reaction for the chlorine. Now I've written them as reductions because there's a reason for this, and I'll show you what that is in just a second. Now, the other possibility is that you get the reduction or the oxidation of water, because this is going to be my oxidation reaction, and form oxygen gas. And another possibility, and this is under acidic conditions, the other possibility is that when we do this reaction, we're going to reduce hydrogen ions into hydrogen gas. And this is our standard potential, our reference potential for our voltages, so this one's 0. So think about this kind of a story here, right? Let's say you were given a job to do, and your job was to roll a ball up a hill. And you have two choices. You're here, and you could either push this ball up this hill, or you could push the same ball up this hill, right? Which one would you choose to do, provided the slopes were similar steepness? Which one would make most sense for you to do, even if assuming you got paid the same amount for rolling this ball up the hill? Well, hopefully you're this guy and says, well, that would be the most efficient thing for me to do. And I would ask you, like, why would that be the one that you wanted to do? And in your head, you would say, well, because it's the easiest. I don't have to move it up here. I just need to get it out of my living room, right? Let's say you have a piece of junk in your living room. Where's usually the place you hide stuff when company comes over sort of unexpectedly, right? You put it in the easiest place. It ends up in a closet, ends up in one of the kids' rooms, it ends up in a spare bedroom. Sometimes you just put it out in the backyard. But really what you're doing sometimes when you're doing that is you're doing the same thing that an electrolysis reaction does. You find the easiest way to do it, and you get it done. And when you're looking at electrolysis, what you look at is you look at the set of reactions that were possible, right? And you look for the smallest difference in energy between the anode here and the cathode here. And that's what the reaction does. Remember, these are non-spontaneous reactions. So you're pushing a ball up the hill. And when you push the ball up the hill, you have a choice of going from here to here, right? You could go from here to here, or you could go from here to here, or here to here. Those are all your choices of how far you could push the ball. Well, a chemical reaction doesn't have feelings, so it just does the easiest thing. So what it'll do is the reactions that'll take place in the electrolytic cell will be this reaction and this reaction. And now all you have to do to know what the cell reaction is flip the anode and add it to the cathode reaction. And in this case, the electrolysis of water with sodium chloride in it doesn't result in the reduction of any sodium because that potential is far too far down, and it doesn't result in the formation of chlorine gas. I'll give you the exception to this in a second, because that voltage is higher than this voltage. Now, here's the thing that makes this a little bit tricky. Let's say you want to do the electrolysis of sodium chloride in water. And really, there's not a reason to do that, but you might use sodium chloride as the electrolyte for the solution, because to do electrolysis you need some ions to flow, and so you might just provide the sodium chloride as the electrolyte. What's going to happen is you're going to have a voltage of about 1.23 volts when you actually start to see oxygen gas forming at one electrode, and you're going to see hydrogen gas forming at the other electrode. But if you want to make that reaction go faster, remember what I talked about, you can make it go faster by increasing the voltage you apply above 1.23 volts. If you do that, though, and a very likely outcome is you're going to have a mixture of oxygen and chlorine at the electrodes, chlorine gas at the electrode surface, oxygen gas and chlorine gas. And chlorine gas being poisonous is probably something you don't want to do. Now, given that the concentration of water in water is really high, you don't get a lot of chlorine because most of the energy will go into this reaction. But a small amount of the energy could end up going into this reaction, in which case you get a small amount of chlorine gas produced at the same time. This actually, and it's beyond the scope of sort of this kind of class, but also points to the idea again that electrochemical reaction rates, the rate constants, are voltage dependent. So you can make this reaction go faster by increasing the voltage. If you increase it enough, right, then this reaction will start, but this reaction will be so much faster by the time you get to 1.36 volts. The major proportion of the gas you collect would be oxygen gas. If you wanted to try this at home and just see how this works, it's very easy to do with a battery, right? I find the best battery to do it with is a 9-volt battery. It's way overkill on the voltage, but in principle, if you can get enough current out of it, you get a couple of wires and you connect them to the ends of the battery. You can hold it with your fingers, and then you take some water and you stir in a little bit of table salt or baking soda, it doesn't really matter. But you need some what's called electrolyte in there. And when you stick these the wires in the solution, you should begin to see bubbles forming at the end of each electrode. Now the electrodes in this case would probably be something like a copper electrode. And at these voltages, on the anode side, the oxidation side, you'll probably start seeing the oxidation of the copper on the copper wire, but that's pretty small. Primarily what you'll see probably is the formation of oxygen gas and hydrogen gas. Another good electrolyte to use potentially is something like vinegar. If you make it acidic, then these reactions all require hydrogen ion, so you get the reactions are a little bit more robust if you use like vinegar or some other acid. Anyways, so that's the idea behind electrolysis. The prediction of the reaction is basically what you do when you are cleaning your house and you're surprised by company. You just choose the easiest pathway. And you notice the way that I did this. I wrote all the reactions out that I thought could be oxidations as reductions and wrote the standard reduction potentials over here. And then all the reduction reactions, I can leave them the way they are, and I wrote their voltages over here. And then you just look to see which is the smallest combination of voltages, which are the two closest in potential. And that's how you know what the reaction is. When you're using a standard reference table, what you do is you look at the reference table and you identify the oxidation and the reduction reactions, and then you can see which two are the closest together. But make sure you're always picking one oxidation and one reduction when you do that. So I want to walk you through the calculation of theoretical yield for an electrochemical electrolysis reaction. Like how much would you expect to get if you did the electrolysis? And this is going to require sort of reintroduction of some units, which hopefully you've heard before, but if not, I'll show you what they are here. So we'll read this question. How many grams of sodium liquid could you create if you electrolyze molten sodium at a current of 15 amps for a period of 1 hour? So the unit you're probably not familiar with, most likely not familiar with, is the unit of an amp. And an amp is the coulomb, so the charge unit per second. So it's how much charge passes per second. So in order to do this calculation, we typically start with a time. You're going to say, I have 1 hour, and there's 60 minutes in an hour, and 60 seconds in a minute. So what I've done is I've created this time now in seconds. I've converted it over to seconds, and now I can use the units to get the amount of charge that I've passed in that 1 hour. So 15 amps would be written as 15 coulombs per second. You can see how these units work out. So basically up to this point now I have charge. The question is, how do you get to moles, right? And the answer is, we've already done it. We know the conversions that we need to do this, and those are Faraday's constant and the coulombs per equivalent. So we need to know N and we need to know F. So F is 96,485 coulombs per equivalent, and N is the number of moles of electrons passed for the reduction of sodium. Now, if you remember when we were talking about it, the reduction of sodium requires only one electron, so the reduction of sodium N value is 1. So I know N is equal to 1 equivalent per mole. So now I just need to set it up so my units cancel. So I need the coulombs on the bottom, 96,485 coulombs per equivalent at the top. And then I need equivalents at the bottom here and moles at the top, and it's 1 equivalent per mole. So notice what we've done now is we've converted all the way from time using current to charge, and then from charge to moles of sodium involved in the reaction. And now all I need to do is multiply by the molar mass, which is 22.99 grams for every 1 mole. And again, just setting this up so the units cancel. So starting with time, I was able to convert over to get to grams. So when I do that calculation, that gives me 12.87 grams. So I've got 3 sig figs. I didn't write the 15 correctly. It's 15.0, so that should really be 3 sig figs. And so I end up with about 12.9 grams. That's a lot of energy just to get 12 grams of sodium. Just thought I'd show you that, though. It's important to sort of understand like the calculations for converting current and time into the theoretical yield of a substance. And in principle, this is how it's always done. Now, it would be kind of a pain. I mean, this works out pretty easy, but for some people, it's kind of a pain to do all the dimensional analysis. They want to have equations. And we're going to do another problem here. But the amount of charge, this is charge, is always the current times the time. Now, I listed the time in seconds, right? So if you're given a current that's not in, or a time that's not in seconds, you have to convert it over, right? And then I is the current. That's generally something that's given, but you can calculate that just as well. To get Q, right, and the relationship between moles, Q is equal to N times F times the moles of material. This will give you charge, okay? So these are actually known as Faraday. They're forms of Faraday's first and second laws of electrolysis. He sort of came up with the relationships that we use for these calculations. But again, these can just be done using dimensional analysis, given that we know what the values for like N and F are. But we're going to go ahead and use these equations for calculating the time in minutes necessary to deposit 1.2 grams of chromium at a current of 12.65 amps. Okay, so how do we sort this information out? One, you need to know the number of electrons required to reduce chromium by electrolysis, and it really has to do with the oxidation state of the metal. Most typically in these kinds of problems, you're going to go from chromium ion or the metal ion to the metal. It doesn't have to be that way, but in these problems it typically is. And so we know that N, right, this value for N is going to be 3. That's 3 equivalents per mole of substance. And then the moles of substance we're going to have to calculate from the grams, right? So we'll have to get the grams, but this will be related to the grams. And then F is Faraday's constant. And so Faraday's constant, again, is 96,485 coulombs per equivalent. And if you look at how the units work, right, this will be moles. This is equivalents per mole, so this is equivalence. And then if I multiply that by Faraday's constant, which is coulombs per equivalent, then I'll be just left with coulombs. And I don't know why I capitalized the equivalent here. I just noticed that. Anyways, sorry. So this will give me the charge. And then I can divide the charge by the current in amps, right? And then it'll give me the time. But the time will come out in seconds, okay? So you have to be a little bit careful with these equations. You have to look at the units and make sure you use them properly. Now, the other thing that I'm going to do is I'm going to show you how you use this using dimensional analysis. In fact, maybe I'll just do the dimensional analysis, and if you want to use the equations, you can, okay? So, because using the equation, just have to make sure you match the units and plug it in, and then you'll get your values. So this is how I'm going to do it. I have 1.24 grams of chromium 3+. So I'm going to start over here. And my plan is to do this. I'm going to have grams of chromium. I'm going to convert that into moles. I'm going to convert that into equivalents of electrons. That I can convert to coulombs, and that I can convert into time using the amperage, the current, and then time I can convert that. That'll be in seconds, by the way, and you'll see this as it works out, and that I'll convert into time in minutes. And I just sort of let the units tell me what to do, but the important thing to remember is you got to know what to start with. And you're going to start with the grams of material given. So I have 1.24 grams of chromium. And so I'm going to convert that into moles. So I need the molar mass. And that's 51 from the periodic table. I don't have these things memorized. I just have one on my background so I can look at it. 0.996 grams for every 1 mole of Cr3+, and then, or Cr, and then for that reduction, right, it takes 3 equivalents per mole to go from chromium 3+ to chromium. So once I have this done, right, you notice the units are canceling like this. I can use Faraday's constant to get to coulombs. So 96,485 coulombs per equivalent. So that'll cancel out. And then 12.65 amps is written as 12.65 coulombs per second. And so now I'm at units of time. And I usually tell people when you see a unit like amps, just like molarity, right? Write out what it is. Like right here in the problem, say coulombs per second. So that'll help you understand how you're going to use that as you're doing the problem. And then I need 60 seconds in a minute. And so that comes out to be 9.10 minutes. Again, you could use these equations, just got to be real careful. Try using them and see if you don't come up with this answer. But you just got to be careful that you do all, like you have to do the mole conversion separately, and then you have to make sure, you know, the electrons in the Faraday, you have those values. You have to make sure current, right, is in amps and Q is in coulombs, and that'll give you time in seconds, which then you have to convert to minutes. So you still have to do a lot of keeping track of units, but if you do the dimensional analysis, it kind of keeps track of itself, right? You end up with minutes at the end, and you know that you finished the problem.